we're going to start with a small presentation to introduce BioSTEAM. BioSTEAM is an open source software, meaning that all the code is available online for you to check, and you can also use it for your own purposes. No questions asked. You can make money off it if you like, and you can extend the tool as well. So it's based in Python. It's programmatic. It doesn't have a graphical user interface yet, but it does have tools for visualization. For example, here we're loading the chemicals. There are over 20,000 different chemicals in the database. And you can access it by whatever name you like. All the common names work, lowercase, uppercase, hash numbers, anything. Yep. So after loading the chemicals, it sets a default property package. I'll talk a little bit more in detail later, but you can also adjust your own property package, use mixture equations of state, and so on. Then you can create streams, unit operations, connect them, and BioSTEAM will take care of creating the system, simulating, as well as providing diagrams. And this is actually how it looks like to use in a Jupyter Notebook. It's been used to assess a large range of bioproduct pathways, which includes going from cellulosic feedstocks like switchgrass and corn stover, new feedstocks with lipids like oil cane and oil sorghum, as well as conventional ones like sugarcane and corn, all the way to diols, organic acids, autochemicals, and biofuels. What BioSTEAM does is after you create the flow sheet, then it's going to run every unit operation sequentially. And for recycle loops, it's going to just rerun those unit operations within that loop over and over again until it's converged. And then it has some numerical methods tagged along to that to accelerate this convergence. The first thing we need to do is define a problem space where we make our design decisions. We have our technological parameters, for example, fermentation performance, titer rate and yield, and contextual parameters like market price, biorefinery siting, environmental impacts. And then we can establish the simulation algorithms. Most of these are already within BioSTEAM, but you might need to design your own if it's like a specialized unit operation. So not only the design, but also the mass and energy balance. And this will provide you everything you need to characterize your sustainability. This includes indicators like economic, environmental, human health, and social indicators. And now there is a lot of uncertainty when it comes to your problem space in terms of, for example, market variability, the performance of certain new technologies you're not unsure of, and the decisions that you can take. So BioSTEAM offers a lot of features for uncertainty and sensitivity analysis. We'll just touch on these more towards the end of the workshop. But the main idea is all your inputs, all your variables, you add a distribution, an uncertainty distribution to it, and then BioSTEAM can simulate hundreds of thousands of scenarios that are sampled from these distributions in order to get your sustainability under uncertainty. Yeah. Now, in terms of techno-economic analysis, it follows the same methodology, right? First thing we need to do is define our problem space. This includes design decisions, right? Experimental data assumptions, financing, taxes, incentives. All this can be plugged into BioSTEAM. Market prices, capital cost correlations. Then we focus on the simulation, which provides our design inventory and material inventory. It includes many different items. And lastly comes the assessment, where we perform the cash flow analysis to evaluate things like the minimum selling price or internal rate of return. Now let's get to the BioSTEAM workshop. So this is the BioSTEAM website. I hope you guys prefer dark mode. I sure do. And we're going to go through the user guide. And as we go through the user guide, I'll be going back to the API reference to look at specific attributes and methods. So first thing we do is import BioSTEAM. And we like to use BST as a shorthand. And when you start creating a process, you need to set the property package. All the system-wide variables like electricity costs, characterization factors, utilities, the chemical engineering plant cost index, as well as your property package can be set through this settings object. So first thing we do is we set thermal, and you can access different chemicals by name. And after you set thermal, you can start creating streams. Here we create a stream by keyword arguments, and the default units of measure is by mole. So kilomoles per hour. I should mention the thermodynamic property package is quite rigorous, the default one, but it doesn't quite work at extremely high pressures and very low temperatures. For that, you would need equations of state, which I'll introduce a little later. Setting the price for streams, we do that through the streams itself. And if we want to get certain results, we can do that through the streams as well, like getting the cost, that cost. Now, these are properties, so they're computed based on the internal flow rate and the price. In process settings, right, this is all through the settings object still. We can change the plant cost index. So if now we're in 2024, right? BioSTEAM, this tutorial was made in 2018, so quite a long time ago. But you will need to update your chemical engineering plant cost index. The electricity price, and these are defaults from textbooks. Cooling agents, this is a list of cooling agents, and you can retrieve a cooling agent by name or just index from the list. Both work. So in a cooling agent, there are many heat transfer related properties. So we have heat transfer efficiency, the heat transfer price. So how much does it cost per kilojoule of heat transfer, and the regeneration price, which is how much does it cost to per kilomole. So certain utilities are based on per material, like per mole or mass. Other utilities are based on the duty. And here we have temperature limit, which is the maximum temperature that the cooling water can go, because otherwise you would have problems in your cooling tower. We also have chilled water, we have heating agents. You can go through this on your own. You can also create your own utility, but for the most part, you won't have to create any utilities or change any values unless you're in your final stages of your techno-economic analysis and you have specific assumptions you want to use. Yes, I see a question or not. Maybe not. Okay. All right. Sorry, guys. I was looking at the chat. Now, the way we create a unit operation is by calling these unit classes and providing them with the input and output streams, as well as key parameters. So for example, flash vessels, they take two parameters, either vapor fraction, pressure, entropy, what else? Duty, and temperature. Any two of those would work. And we initialize unit objects without actually simulating them. So if you do .show after you initialize the object, it will not have the output results. For that, you need to simulate it. And then to get specific results for unit operations, we use .results, the method, and it provides a data frame. It includes all the utilities, the design parameters that were necessary to calculate the purchase cost. And if you want the installed equipment cost, that's also available, but it's an optional argument here in results. Okay, so those are unit operations. Now for recycle loops and for systems, we'll need to first create streams, then the unit operations, and lastly, create the system. So here I haven't created the system yet. Here I'm just taking the flow sheet and making it spit out a diagram. Now you might notice how streams here have dashed lines. That means that they're empty, and the feed here is not empty. So now to create the system, you can use the main flow sheet to .create system. There's a lot of ways to create a system, but if you're a beginner, this will be the main way that you would create a system. It takes in all the unit operations that you've created until now and formulates the system. The system object looks very similar to a unit operation. It has its inlet and its outlets, but it contains all the units within the object. After we simulate, we get some information on convergence. Now, when you look at highest convergence error among components in recycle, if you don't know what this means, you might think it's a warning. It's not. What this means is it successfully terminated under a given tolerance. So it's accurate to the point of the default tolerance. And you can also change that tolerance to make it simulate a little more to get even higher accuracy to the absolute steady state. System also has a results method to look at general results for that complete system, like the utilities, the purchase cost, installed equipment costs, utilities, and so on. And if you want a full report of all the design requirements, utilities, even cash flow analysis, which we'll talk about soon, then you can use the sys.save report. Any questions there? Okay. All right. So that's the intro for how to use BioSTEAM. Now, BioSTEAM has a lot of, I guess, streamlined techno-economic and lifecycle assessment tools that you can use, as well as ways that you can extend the platform to use it for your specific technology. I'm going to talk about unit operation results and how to create your own unit operation. So the unit operation results will give you a better idea of how a unit operation is structured. And then we can go into how to create your own. Ignore all that words. Let's see. All right, here we go. So let's, as an example, create a distillation column. BioSTEAM has lots of distillation column models, including a simple model for binary distillation where you separate two components based on volatility, of course. It has a shortcut column, which allows for multi-component distillation, but it will not give you an error for azeotropes. It might not be as accurate, but it might be accurate enough for your system. And the third one is a mesh-based rigorous column model. And it goes through solving all the equations and all the stages within a distillation column. All right. Now, if you like a little bit more references or details on distillation, you can go to the API reference in units, and there's a list of different documented units. There's also some units that have not been documented yet, like fluid catalytic cracking for pyrolysis oil. But let's go to here, distillation. We have the binary distillation right here, the shortcut column, and here are all the input variables, right? Input parameters and some examples that you can use. You can just copy this guy, right? All this code, paste it on yours, and then just replace it with your own specifications and mesh distillation as well to unit operation results. Okay, so after we create the unit operation, we can also form a diagram from the unit. So dot diagram. And this is a little different than flow sheet level diagrams or system level diagrams because it shows you all the internal unit operations within that module, right? So here we have the vessel, distillation column vessel, a condenser, the reflux drum, the pump for the reboiler, and the split for the boil up. All this is modeled within that unit operation. Now, the actual results are stored in design results in dictionaries within the unit. Purchase cost, a list of heat utilities, and a power utility object listing the total consumption or production or both. So later on, when we talk about how to create your own unit operation, you'd be filling up these dictionaries with your own results from the simulation. Okay, also the auxiliary unit operations that I talked about up here, right? We can access those as well. So here we're having a look at the condenser. After simulation, some of the colors might change, right? Because it's fun. The condenser turns blue, so anything that where the duty is negative turns blue. Anything where it's heating up turns red. And the streams, the thickness are based on the amount of flow rate. All right. And when we look at the design results, we see that it's populated with our design results, the purchase cost, and our heat utilities. Now, you might be asking yourself, how do you create a heat utility? It's very simple, and we'll talk about it. All you need to do is just provide the unit operation, the temperature, and the duty, and it'll automatically create the heat utility and add it to the list. And all that is done internally, right? And here we have a look at the results for the distillation column. There's also additional dictionaries like the units dictionary, and that's how BioSTEAM knows what units of measure go into this results table. Okay, I think that should be all. Here's a fun plot. Certain unit operations has special methods that you can use. For example, for binary distillation, you can plot the stages in the McKay-Thiele diagram. All right,
Can I ask a
yes.
question, Yuri? Yeah. So basically, for the distillation, the back end is Macabitiel. So it's only for binary systems, right?
For this unit operation, yes. Now, there's also a shortcut column and a rigorous column. So rigorous columns work for anything. Shortcut columns work for most cases, including multi-component distillation, but it'll not work well for situations where you have azeotropes. Yeah, mesh
So
distillation
the
is
rigorous is basically like Underwood,
no, that's not rigorous. So Underwood, Gilligan, Fensky, Underwood, Gilligan, that's the shortcut column, right? For rigorous, it's things more like inside out, Russell's inside out algorithm, or Wang-Hang's bubble point algorithm.
Thank you very much, Yuri.
Mhm.
You seem very, very knowledgeable about this. It's very interesting.
My pleasure, my pleasure. Okay, we got one more question. I think Kay raised the hand. I can't hear you, Kay. Maybe no question.
To export a system as a file, like for instance, you create a system from a flow sheet. Is it possible to export that as a file which you can share with other people? And if not, what would you recommend for sort of collaboration between multiple users for one BioSTEAM system?
Yeah, I highly recommend GitHub, right? Push and pull your changes often, and you can work together like that. Yeah, having a specific file, right? The Python files are the files in a programmatic sense. Thanks for the question. All right, now let's go past unit operation results into inheriting from unit. Now, I'm assuming that most users here are working on a project that requires a little bit of flexibility, and you might have unit operations that are not within BioSTEAM, or you want to simulate a unit operation in some specific way that is not available in other process simulators either. So for those cases, we can extend BioSTEAM a little bit. So this is a diagram of the structure of a unit operation. A unit operation has all these default variables that specify how does the unit operation work. So the number of inlets and ins, the number of outlets, even equipment lifetimes, and that feeds into a TEA object, which I'll talk about later. And also abstract methods like run, which decides the mass and energy balance. You would take your feeds and your specifications and adjust the outlet streams accordingly. You also have the design method, which is meant to populate the design results dictionary, and the cost method to populate the purchase cost dictionary. So this gives you everything you need to design and cost a unit operation. And here's a very small example. What we're going to do is create a boiler that takes in one feed and outputs the vapor and the liquid product. And we'll specify vapor fraction and operating pressure. So here we're specifying the number of inlets, 1, number of outlets, 2. Now the units of measure, that's just to get the results table with units of measure to make it prettier. It also helps for bookkeeping too. And now we define the abstract methods. So here in init, if you ever subclass anything from Python, you would know about magic methods like the double underscore, init, double underscore, where you set initialize an object. This is very similar, but we don't need to define all the default input parameters like the ID, the ins, the outs, what else? The thermodynamic property package or any of that. So this is just the additional parameters that your unit operation is going to take. So in this case, the vapor fraction and the pressure. Now in run, we access the inlets. You could have also done self.in0, but feed always works as well. The outlet streams, vapor and the liquid. And then here we perform the vapor liquid equilibrium using the stream objects. Stream objects have a lot of capabilities. It's not just a place for storage of the temperature, pressure, and material flow rates. It also has things like methods to compute any mixture property, enthalpies, mass and energy balances as well, mixing, and vapor liquid equilibrium, liquid liquid equilibrium, as well as VLE, vapor liquid liquid equilibrium. Okay, so then we use another method here where we copy all the data from the gas phase of that stream and the liquid phase of that stream into the outlets. This might seem a little foreign to you. If it is, I recommend reading the ThermoSteam 101. That'll give you a lot more details on stream objects. It's quite powerful. All right. Now for the design, what we're doing here is we're adding a heat utility. And BioSTEAM will take care of choosing the correct heat utility that'll meet your duty and your operation temperature. It does, right, uses a countercurrent assumptions and accounts for the temperature limit of your cooling water if you're using cooling water, phase changes, everything. Now here we're getting the temperature of your utility in order to get the temperature gradient. We have some assumptions on heat transfer coefficient. We can get the area, and we set the design result for the area. We can also add the number of parallel units. So if the whole unit, there's like several in parallel, you can write self. Otherwise, if it's like a subunit, you can write the name of the subunit. You might be asking yourself, how do you define a subunit? You just need to be consistent in your baseline purchase cost. So parallel just makes this cost n times. I might be moving a little quick here. Any questions?
I had quite a few questions about the inheriting
please.
from unit. Is it always on top of what's in the source code? Or do you need to, for every single one that you do you need to initialize it and do the the cost function and the design function?
Yeah, I think there's, here, let me show you this. So there's a lot of unit operations in BioSTEAM related to bioprocesses, including aerated fermentation and so on. If you're working with a bioprocess, you most probably won't need to define any unit operation yourself. You can just use the unit operations in BioSTEAM. And you don't need to subclass from these units, right? Everything is already defined. The mass and energy balance, design, and cost.
What about for a reaction? From
For
what
a
I can
reaction.
understand, if you want to, so I've been working with a stirred tank reactor, and the documentation for the stirred tank reactor went straight to inheriting from a unit in order to do a reaction. So I haven't been able to avoid as much as I wanted to
Yeah.
inheriting from a unit.
I see. That's a great question. So the stirred tank reactor is actually meant to be subclassed.
What do you mean by subclass?
Subclass is where you, let me pull it up real quick. Subclass is this right here, right? So when you're inheriting all the attributes methods from the parent unit operation. Now, there's some other units here that work out of the box. Now, Rebecca, I think what you should probably be using is the aerated bioreactor. I'm assuming it's aerated. If it's not,
I'm modeling. I've got a two section model that I wanted to do. At the moment, I'm doing the fermentation to create a PETase, so an enzyme that breaks down PET. And then I wanted to model using that enzyme to break down PET. And that's where I'm stuck. I'm stuck with the stirred tank reactor of using an enzyme to break down PET.
Yes. All right. So, Rebecca, I'm going to send you an email after the workshop with easier instructions of how you can go about it.
Okay, thank you very much.
Absolutely.
Thank you so much.
Could I ask a question while you're still on
questions?
this, yeah?
Go ahead.
So if we want to change the stoichiometry of the reaction that we're seeing here, is that so? Is that what the X perhaps is referring to? Or so, for example, if we want to make, I don't see biomass as a product here, but let's say that we're producing
Yep.
biomass. We want to make it sort of like less efficient, so we need more glucose per biomass or more
Mm,
oxygen
mm,
per biomass produced.
Okay. I'm gonna answer your question a little bit incompletely, and then I'll go more in detail as we go into the case study for microbial lipid production, in which
Fair.
I think I included biomass production, but if not, I'll send you a link where this is done, where we're
I mean,
including biomass production and other things, and you can use that as a reference.
yeah, you can skip it entirely, by the way, if I'm jumping ahead and you're gonna go talk about this a bit later. So, up to
Sure,
you.
sure. Yep. Now I should mention reaction objects. These reaction objects, you can define a stoichiometric reaction. Now, this stoichiometric reaction, it's unbalanced. You can balance that with this keyword argument. And now the extent of reaction is based on your limiting reactant, which you define here. Then that can get plugged into unit operations that accept it, like the aerated bioreactor. Okay, we'll go back to inheriting from unit. Where are you? There we go. All right. So here we're using our own cost correlation from a certain textbook to compute the purchase cost. Then we input the purchase cost as an item in this dictionary. And if we have different material, pressure, design factors, or bare module factors, right, in order to estimate the installed equipment cost, which includes like foundation, control, piping, construction, all that, then we can add that here. So these are all the different fudge factors that come into the capital cost estimation. Now, here is where we tested. We created the boiler object. It just appears as a box because that's the default graphics. You can get creative and change the graphics, but I think no one really cares about that. All right, so after simulation, now let's look at the results. We do dot results. We get our utility, which was calculated with that line add heat utility, and when you gave it the duty and the temperature. We have the area, which you populated yourself, the purchase cost of the boiler right there, and the utility cost. Now, here is another small example. If you have an extremely large flow rate, because we defined here a maximum value for the area and we added units in parallel, then it's actually going to take that into account. Let's talk a little bit about reactions. So here we're going to model this stoichiometric reaction, which is transesterification of a triglyceride to produce biodiesel and glycerol. We are not going to create our own chemicals, but use a set of chemicals from a biorefinery. And a lot of biorefinery models are available for you to use with pre-made chemicals, including hemicellulose and cellulose, or I should say that the actual fractions, silane, glucan, and so on, sugar, many things. So here we have, if we go to API references biorefineries, here's a couple of the biorefineries that are available. For example, cellulosic, right? And so on. Let's see here, systems. And you can even create subsystems that are employed in these biorefineries for more modular and to be able to reuse code, not necessarily copy and paste. Yeah, if you're interested in any of these, you can go through these. And they usually have a paper that has the actual detailed design and assumptions. Okay, I think Kay has a question.
Yeah. How do you define your own biomass for your own organism if it's not already in one of the pre-made biorefineries?
Okay, biomass. So that's a fun one.
I guess to clarify, how do you create the chemical corresponding to a given organism's biomass? Because it's not like a more simple chemical where you can go into thermosteam and use like a smile string or something. But what did you do for defining the chemical of the organisms that you're using in these biorefinery models?
That's a great question. I think we can go through them now. All right, so I'm going to give a little bit of a tutorial on chemical, and then I'll answer your question. So chemicals, they're created when you do set thermal, right? But you can also create them yourself and then pass that to set thermal. So here we're creating a chemical from the database water. It has all this data and much more. This is just like a preview data for the main properties. And also you can make sure that it's the right chemical. That sometimes different chemicals have the same common name. Okay, chemical objects also have these property objects that you can call and get estimates of that property. For example, the vapor pressure, you can call and get the vapor pressure, surface tension, motor volume, and so on. Some are dependent on the phase, right? So volume is dependent on the phase. Surface tension, that's just water and liquids, and vapor pressure, that's between water and liquid. I know, why am I explaining this? Okay, now this is just a quick look at the vapor pressure model, and you can have a look at what method is being used as well. And you can change the method. There's like a list of 10 different methods available, and there's a lot of data from different sources, that are added to each property object. You can also add your own methods. So here we're adding a new method for the vapor pressure, and it'll automatically set that as the method that you're using, the user method by default. You can also add a name if you prefer not user method. Yeah, and here's a list, for example, of all the methods for the heat capacity, and we always use the most accurate method. All right, so with that in mind, we're gonna skip the rest right there, and we're gonna go to property packages. All right, now here's an example. Here we're creating a chemical called lignin and giving it the main properties, right? Heat capacity and density. We're telling it to default the rest of the properties like viscosity because we're not too interested in it, or at least not at this stage of the techno-economic analysis. And we're providing a formula. So to answer your question, okay, we should pass the formula and the chemical object will automatically set the molecular weight. And when you plug that name and when you make the reactions and also pass correct atomic balance equals true, then whatever reaction you have for the biomass is going to correct it based on the formula. I should also mention that your atomic balance does not need to be correct. You can have it by weight as well, because sometimes we're not too interested on, for example, do we meet the amount of magnesium in the chemical formula? Yeah, okay. Now,
Thank you.
Excellent. I'm happy I answered your question. Here's another chemical called dry yeast. And because this biorefinery, these chemicals that are used to model a biorefinery does not account for the atomic balance in the biomass production, then it's okay to just say molecular weight equals 1. Okay, one more thing I should note is when you're creating a new chemical and it has a certain phase, so it's gonna always remain, for example, if it always remains as a gas, then you should pass phase equals G. Or if it always remains as a solid or a liquid, you should pass phase equals S or phase equals L. And this just speeds up simulation and decreases the number of variables that you need to input to your model. So if you were adding, let's say, lignin, and you include the gas phase and the liquid phase, you would have to add the vapor pressure, the surface tension, and all these other variables that really are inconsequential to your simulation, but you'd still have to add them to tell BioSTEAM how to perform the vapor liquid equilibrium. So to summarize, always pass the phase if you can.
Is there place to put the solubility of the chemical?
Solubility,
It's quite relevant for gas fermentation in particular.
Yes, gas fermentation. Here, gas ferment. So you mean Henry's constant?
I'm actually not sure how I would express it, but for example, for hydrogen, you'd have like a certain milligram per liter. I think hydrogen is like 1.5 milligrams per liter at room temperature approximately, or 30 degrees Celsius.
That's right. So what you're thinking is Henry's constant. And this does work for vapor liquid equilibrium. I have a bioreactor model where we have hydrogen and CO2 producing acetic acid. Now, I can't exactly remember how the Henry's constant was added, but I can check real quick. Let me see. All right, bioreactor source. Okay, here we go. Okay, all right. So Henry's constant is basically a special case of the vapor pressure. So you would add that Henry's constant to your PSAT chemical model. Now, in general, though, if you don't add any Henry's constant, you should still get good results. And you can double check the concentration of hydrogen you get in your liquid after the simulation of the vapor liquid equilibrium with the Henry's constant and make sure that the values are more or less similar. If they're not similar, you can do two things, right? Add your own model or post an issue on GitHub. Yes. Now, regarding the modeling of the bioreactor, I highly recommend you check out this gas phase bioreactor and this example right here. I think it'll save you a lot of time.
That's actually one of the processes that we're interested in modeling, so that is perfect.
Perfect. All right. So that's it for inheriting from unit. We should probably go to techno-economic analysis.
And also, I have a quick question related. Before going to TA, so I was also trying to get some like data for like price. Can you recommend some kind of reliable
right.
web page or something for that?
Man, yeah. Like at this point, we're consulting, but that's totally cool.
Thanks, man.
Yeah, no problem. There is a website, I think is ChemCat or something like that.
MCAT?
Materials like CAT cost, sorry. ChemCat Bio. It has a lot of good prices. I use this one all the time.
I see, perfect.
Other than that, you can check textbooks or past
Okay.
publications, and they usually have prices.
Amazing. Thank you so much.
Yeah, no problem. Any other questions? I feel like I'm on a roll here. All right, cool. So now TEA objects. TEA objects are abstract classes.
I
So you
had a
need.
question I put on the group. I don't know you saw the chat.
Nah, I haven't seen the chat. Okay. Can I adapt BioSTEAM to simulate pyrometallurgical, like HPAL for PCB recycling? Honestly, I have no clue what are the pyrometallurgical or hydrometallurgical methods. Never heard of them. This sounds like a mechanical process, I think. Am I correct?
Well, so there's different phases for PCB recycling. They're like different combination of phases.
Okay,
So
okay.
there's some phases that has to go through mechanical separation, so shredding. And there are other phases that would have to go through like electrolysis, smelting, the furnace, and these kind of things.
Yeah.
So they will have some form of chemical reactions.
Mhm,
So I tried
in
using
theory.
yeah.
Oh, go ahead. So in theory, you can do all that in BioSTEAM. Now, whether it's facilitated, that it might not be as facilitated as you need it to be. You can explore other options, but BioSTEAM is a viable way. Here at the University of Wisconsin-Madison, also at Iowa State, they started using BioSTEAM without my help, and they were able to create systems for waste plastic recycling. And this includes like shredders and all sorts of unit operations that I haven't modeled. If you have the right literature, you can plug in everything in BioSTEAM, and BioSTEAM gives you that flexibility to model things the way you want it to and to streamline the TEA and LCA, which is what you need. If by any chance you have a process simulator that provides the cost for some special unit, you could plug in a surrogate model in BioSTEAM, and people have done that. I hope that helps. I can't really help too much on this.
Yeah, one of the problems I tried to use this in BioSTEAM, but one of the problems I had was with the YAML files of the reaction.
Yeah.
So I had a lot of problems with the species name, the thermal. So sometimes, I could state that a particular process is a gaseous process, and I could have an ideal solution. But I also tried other libraries like Cantera. That was I had serious problems with that. So, I don't know. It's something that I think maybe I'm not going through the right approach, because for each particular process, it's like one moves from A to B to C to D all the way to the end. And as the process changes in phase, it also has to give off some off gases, you know. Unfortunately, chemical engineering is not my background, but at least I should be able to understand the basics. So
Yep,
that
yep.
was where I ran into a lot of problems, especially in converting from one phase to another and what is expected in the chemical reaction, and also the waste as well from the processes that comes off that.
You need to write out the mass balances within the unit operations that you're making. It sounds like you have data for what you're expecting the splits to be within your
Yes.
outlet streams.
Yes,
You can
correct.
just plug all that in. You can also define chemicals with a single phase and call it things like PCB gas, PCB liquid 1, PCB liquid 2, right? And then within when you're writing your mass and energy balances, you convert from one PCB to the next, and that'll help you keep track, right? Yeah. Try to get creative in how you detail your mass and energy balance according to how you envision your process to work, right? Don't try to fit your process to BioSTEAM. Try to fit BioSTEAM to your process. I hope that helps. All right, now techno-economic analysis. There are lots of different ways people do TEAs, and almost every TEA is different, but they all have the same framework. Because of this, we left certain methods abstract, including the TDC method, which stands for, what's it called? The total depreciable capital, the fixed capital investment method, and the fixed operating cost. So for this particular TEA, the way they did it is simply assumed that the installed equipment cost is a good estimate for the direct permanent investment and for the fixed capital investment. So they really didn't think too much about it. For the fixed operating cost is some function of the fixed capital investment. So all these are just fudge factors, and that's mainly how it works when you do TEA. It's a lot of fudge factors. Okay, so once you've defined these abstract methods, then you can create your TEA object and you make sure to pass your system. So with that, you can perform the cash flow analysis, and it's as easy as a single method to do the cash flow analysis. You can also estimate things like production costs, solve the price for your feed or your product to get your minimum selling price or your maximum feedstock purchase price, solve for the IRR. And yep. Then there's another section here on incentives. Yeah, let's not go over incentives. I think this is good enough. Any questions on TEA?
Hi, yes. I have a question, and I don't know if you'll cover this if you cover the changes to operations, but how do you have a cyclical change? How do you have like a cyclical change in operations be reflected in a TEA that you do using BioSTEAM, especially if you update it with parameters week by week by week by week for 30 years?
Yeah, that's a tough one. There's no easy way to do that in BioSTEAM. Not yet. I could come up with a way and get back to you in a week, but I'm a little busy. What you need to do is go in the code and do a little bit of development. Let me see if I can find the source code for TEA object. Here we go. So somewhere around here where you compute. Yes, this method here. So this method computes the costs and the revenue and everything year by year. So it's a whole table inside this method. Somewhere in here, you need to change the sales or the cost to account for those cyclical changes year by year. or week by week. Now, this is just for the TEA part. If you want to skip the simulation, for the simulation, there is a way to do it on a yearly basis. Oh, does that make sense? Well, to operate a system differently throughout a year. So let's say during the first 3 months, you're processing a certain maybe switchgrass, and then this other 7 months you're processing corn stover, right? The compositions will change. You might even have different unit operations. You can do that in BioSTEAM. It's called an agile system. Do I have it here? So there's the system object. So agile systems are not documented yet, but they're actually not too hard to use.
Thank you. I've sort of tried using the agile system, and it worked when I was varying the amount of time within a year. For say, I was changing the flow rate. It worked for the amount of time within a year, but if I went beyond a year, that's when I got like issues.
Yes, you can't. It's only for a given year. There would need to be additional development to account for that.
Okay. Thank you so much.
All right. I hope this helps.
Yes, it does.
A question from my side on the capital costs. Do you have some list of equipment and the equipment bare module costs somewhere that we can access? And is that also something that is being updated over time?
No, it's not updated over time. But if there's more data, then we add that in, right?
Well, that's what I meant. That's what I meant by updated.
Yes, for bare module costs, the way they're coded in is at each unit operation. So if you have a question on bare module costs for maybe the shredder or the stir tank, usually they're in the source code for that specific unit.
Okay.
Now, if you're looking for bare module costs in general, I recommend like senior design textbooks. Basically, every senior design textbook has a lot of bare module costs, including Warren Sider's textbook. I really love chapter 16 on the economic analysis.
Yeah, I think we are using that textbook and a few others. It also has scaling factors, so we can build it up like that. But it's also nice to have some sort of like empirical data when it's available. And so for some smaller scale equipment, we have like vendor quotes. I was wondering if there might be a database like that in the back end of BioSTEAM.
Oh,
but it
vendor
sounds like
quotes. Yeah. I see. No, there's nothing on the, well, for some unit operations, yes, but we don't list out like who the vendor is or anything. We just leave that blank. We don't have a list. It's just per unit.
Yeah. Okay. Yeah, you answered the question. So basically for each unit operation, I can find it embedded in the actual unit operation. There's not like a standalone list dictionary that's being. Okay.
Yeah.
Thanks.
It would be nice to have something like that, but yeah. Okay. All right. So that's TEA. Let you read all these other parameters that go into it: depreciation, schedules, the duration, income tax for Lang factors. I trust that you'll read up over what is a Lang factor and so on. All right. So the test case, you can actually use BioSTEAM from an online server called Binder. So if you open up here, How to Steam, click on that, it'll open up this tab. And you can go to case studies. There's also problem sets and solutions. Is it down? Yeah, I think we need to reopen it. It does take a little bit for binders to open. Just give it some time. And this was actually fairly quick. There we go. So we opened up the aerated bioreactor tutorial. What's going on here? Oh no, I opened the picture. All right, here it is. So in this case study, we are taking a solution of glucose that comes in at a specific composition. This could be coming from, for example, after hydrolysis of biomass, or it could be coming from a sugarcane juice. And what we're mainly focused on is modeling the fermentation. So here we have a multi-effect evaporator for dewatering optionally, and here dilution water coming in. So depending on what feedstock concentration comes in, you might want to evaporate or add dilution water. Then here we have our aerated fermentation. It's a stirred tank, a recirculation, and our compressor, our cooling heat exchanger for the compressor because that heats up the inlet air. And yeah, so for aerated fermentation, the oxygen uptake rate is very important, and the oxygen transfer rate must be equal to the oxygen uptake rate. I'm not going to go in detail on how this works, but the main idea is that we need to estimate the what's it called? KLA, the mass transfer coefficient, in order to model the fermentation. So there's many methods available within BioSTEAM, including the Riet method for stirred tanks, as well as for bubble columns, we have other methods. And we're going to design this as a stirred tank, not a bubble column reactor. And we can decide on the agitation power, and the dissolved oxygen concentration typically is 0.5. Other key parameters include the operation temperature, the maximum temperature drop in the loop, heat exchanger loop. And if your energy balance is not, well, typically for fermentation, you're producing a lot of co-products and biomass and burning a lot of the feedstock. So your energy balance is not too exact if you do the enthalpy out minus enthalpy in. It's just difficult to model. In those cases, you just add the given duty per kilomole of oxygen consumed. And this is typically how aerated bioreactors are modeled. Here are 3 equations where we have the production, growth, and respiration, and we're going to model those equations too. And here's some additional parameters. So after creating the chemicals, we can create the reactions and pull all those reactions together into this fancy reaction system object that allows for a single object to represent all the reactions together. So here first, we react glucose to produce these guys, and then right after that, the remaining glucose gets consumed to produce biomass and carbon dioxide. Now we plug all our design specifications in, and we're setting this to batch. And after, so here there's also another, what we call a process specification, which overrides, or suppose before the mass and energy balance, it'll run this. This is helpful if you have like a big system and you want it to adapt according to certain design specifications. So here we're adjusting the titer according to whatever performance, titer and productivity we have. Sorry, we're adjusting the residence time as well as the yield. And this can help for sensitivity analysis later on. The diagram doesn't appear. That's kind of silly. Let's run this, guys. It'll take a bit for the diagram to appear. Now, after we create our fermentation, right? And this is our fermentation and includes the compressor, the cooler, and so on. Let's create the rest of our unit operations, including the multi-effect evaporator, mixers, and the lipid extraction system. So here we're using a function that creates a system from one of the previous biorefineries, just to make things quicker. Then we're creating the system from the unit operations that we've created. We simulate and then get the diagram. So let's run this guy too. Now there's also a specification here that adjusts the amount of dilution water or evaporation rate in order to achieve your titer. And you can read up on this on your own. And here we go. Here's the complete system with dryer, well, with the centrifuge, drum dryer, screw press, everything you need to separate out the lipid from the cell mass. And there we go. Lastly, we're using a TEA object that is previously made in the biorefineries. So create cellulosic ethanol TEA, takes in the system, and uses all the default assumptions from the past TEA. Now here we have the TEA object. We solve the price for a liquid product, and that's actually a reasonable price for the lipid. And down here, we're performing a sensitivity analysis. Now, I won't go in detail about the code, but the main idea is that BioSTEAM has some tools that you can use to make these plots a little bit quicker rather than coding everything on your